Welcome to everyone. I think it's time to start. Welcome to our Littelfuse thyristors training. My name is Thomas Bolz. I'm the product manager from Rutronik for thyristors. I will moderate this seminar today. Today's webinar is entitled Littelfuse thyristors training. This is organized by Rutronik. Our supplier Littelfuse offers most comprehensive SCR TRIAC portfolio on the market. Therefore, Littelfuse and Rutronik makes a customer seminar on this issue. Our presenter is Pablo Cortez from Littelfuse. Hello, Pablo. Thank you for your time today. Please, can you introduce yourself?
Thank you, Thomas, for this opportunity of having this training here at Rutronik headquarters. My name is Pablo Cortez. I'm the head of the FAE group, FAE Field Application Engineering in Europe.
Okay. Pablo, one question. What is the intention on this training? Why we are talking about TRIACs?
Nowadays, there are many electric loads that need to be controlled still with a most efficient way, a most efficient or cost-efficient way, which is basically TRIACs and bipolar devices. We have a new series that we have launched several years ago, and it's really tackling the, let's say, the challenges we see in the market of new design challenges when it comes to control those electric loads. These are actually the QV and SV series.
Okay, this is all from my side. Please, can you take over?
Yeah. So first of all, let me just go through the agenda quickly to understand what we are going to discuss today. So first, we're going to see at the application and types of loads to be controlled with the TRIACs and SCRs. We are going to differentiate between resistive and inductive loads. Also, we're going to see the different strategies that we can find out there in the market between an electromechanical device and a semiconductor-based solution. Secondly, we are going to look at the low power SCR and TRIAC portfolio. Again, we are going to have this deep dive in QV and SV series, which actually help us to understand how we are going to decrease the bill of material cost, how we're going to increase the DVT robustness while using these devices. So this is an overview about our solutions, how basically our solutions look like when it comes to thyristors, SCRs, and TRIACs. We really come from the very low power milliamp, let's say, arena to the kiloamperes, from very low packages or very low, small packages to press pack thyristors. So today's training is going to focus on these two segments, QJ and QV, SGS and SJ discrete devices. And yeah.
So questions about the seminars?
Yeah, sure.
Okay. Oh, sorry.
So yeah, Thomas, please, if you want to.
Yes, okay. I want only say, okay. There was the rules are, okay, sorry. One rule, the duration is 1 hour. If you have any question, you can take the chat on the right sidebar. We will answer at the end of the seminar. We have a question answering of slot of 10 until 50 minutes. And if you have any further question, you can contact us later, like it is written here on this slide. So sorry, Pablo, no you can take over.
Yeah, we were discussing about the portfolio we are actually offering and where we are going to focus today on the training. So first part of the presentation of the training is going to be really focusing on QJ and QV TRIAC series. The applications are written there: motor control, water heaters, LED dimmers, coffee brewers, and in general, more kitchen applications where we can also access some industrial applications. So what we can find in a standard kitchen is something like between 25 to 30 loads, electric loads to be controlled. And we can differentiate those loads between resistive and inductive. In this particular case, what I'm showing here is that water pipe, we actually need to control the water temperature, actually to boil that temperature, that water. And normally it's basically use a resistive load. And this can be controlled with a semiconductor. In the second case, it's a oven. Basically, in an oven, you can find in the chamber two different loads, one on the top, one on the bottom. And those loads, again, can be controlled again with the semiconductors, right? On the inductive load part, we see some motors, mainly basically motors, AC loads, AC inductive loads, also to be controlled. What kind of loads we can find, so sort of pumps and compressors that actually are there, and again, just make a number of between 25 to 30 loads in your kitchen. We're gonna look briefly on this inductive load first and try to differentiate to understand what kind of loads we will find as inductive in a kitchen, for instance, right? So we're going to differentiate between BLDC or permanent magnet motors that at certain conditions, these motors will be more efficient than a standard asynchronous AC motor. This has a significant impact in the positive impact in the eco-directives. However, they really require an inverter that actually to be operated, so to operate those motors, and this means an additional cost, right? Where there are many other loads like AC motors, AC asynchronous motors mainly, that can run at read frequency and voltage and can be disconnected with an electromechanical relay or a simple semiconductor bipolar device like SSR or TRIAC from Littelfuse, for instance, right? We're going to look first, and before moving into the portfolio, we're going to understand the benefits of a semiconductor-based solution against an electromechanical-based solution, right? So first of all, when we look at relays, electromechanical solution, we have moving parts. So basically, reliability is a topic to be really considered because the contacts will be moving, and of course, they can get welded. I mean, this is, of course, a potential issue, a potential challenge for designers when it comes to calculating the lifetime of relays. Inrush current is another topic because we cannot control. There are some techniques, but in general, those techniques will require additional cost. Of course, noise, I think it's very naive and very evident that if we have 25, as I told you, 25 to 30 loads, if we have relays all around in your kitchen, this will be very annoying, and this is for sure unwanted. And of course, EMI generated, because the relay can turn on and off, and no matter where the sine wave can is actually located, the current and voltage, and it can actually generate EMI also into the electronic system. The advantages of a semiconductor-based solution, I think, are clear: higher reliability, lower inrush current because we can control the duty cycle, so-called firing angle in the triad. Low noise, or basically no noise, and low EMI generated because triacs and SSRs in general, they turn off by zero current crossing. Of course, this will not generate a lot of EMI, right? The clear disadvantage of a semiconductor-based solution is that they require electronics, control electronics, and potentially it's the so-called snubber, which is basically a resistor and a capacitor network that needs to be used in some applications within a triac. So first of all, before moving on and before understanding more about the application, let me explain what a SSR and a triac actually are. These are bipolar structures that can actually block in both directions when there is no current, no voltage present at the gate, and basically will not conduct current in any direction. So if we apply a positive current to the SCR, so the silicon control rectifier, or a triac, which is more a bidirectional SCR, we can find monolithic, by the way, monolithic triacs, or basically a triac made out of two SCRs in a back-to-back configuration. Anyhow, if we have a positive current, we can control the load current in this positive sine wave, right? If we apply negative current to it, the triac, which is a bidirectional device, will control the load in the negative direction, where this SCR not, because it's the simplest, was just basically one unidirectional device. Okay. So we're gonna first look at our portfolio to understand the parameters, the factors that actually are used to in each application. So the Q and S series is more the existing the portfolio of Littelfuse for triacs, which starts with a Q, and SCRs that starts with a S. We have more than 500 active parts, so you can understand we have a very broad portfolio between 600, 800, and 1,000 volts. Maximum junction temperature is 125, and they are very cost competitive devices. Some years ago, we launched the QJ and SJ series, We have more than 200 active parts from 400 up to 800 volts. Mainly, you will find devices between 600 and 800 volts, because 600 is for single phase configurations, where 800 volts is the voltage range that is going to help us on three-phase configurations. So we have a new passivation design introduced in this technology, which help us to go to the 150 junction temperature, which will allow customers to decrease the thermal management efforts, right? Because we have 25 degrees more available at this technology, right? And our latest and the real focus of this training is the QV and SV series. Nowadays, just 80 parts, but we are extending the portfolio right now. We have 600 and 800 volts as main focus. As I told you, 600 will be for single phase, 800 for three phase. Of course, we will see particular design challenges everywhere, but this is the mainstream. We are going to use the same passivation design that QJ and Q and SJ uses. We will allow designers to go to the 150 degrees, but we have also new gate design will help us and will allow customers to go to higher DVDTs, which is an essential parameter in TRIACs and SCRs designs. And I will explain you right now why. So before we understand the DVDT challenge in the applications, we need to differentiate between two. So first is the DVDT at commutation that will happen whenever we are switching off the TRIAC or the SCR that can actually, due to this high DVDT, turn on again the SCR in an spurious manner, so an unwanted manner, because we actually remove the gate signal and we want the TRIAC to be off. But this can actually be reactivated due to the DVDT at commutation. Okay. Before we move on and understand the second part of the DVDT, I will explain why DVDT at commutation is more important in, or more, let's say, have a significant role in inductive applications. When we have in this example, this resistive load for a oven, for instance, to heat the chamber, it's basically a resistive load. In a resistive load, we're going to have voltage and current in phase. So the TRIAC or the SCR will switch off at zero current crossing. You can imagine, and you can see here in the picture, DVDT at this point is going to be very low. We don't really need a DVDT robust product, right? Whereas if we have an inductive load, this will be different, and current and voltage will not be in phase. There will be current actually leading and voltage lagging. The physics remain, and the TRIAC will switch off at zero current crossing. And you can imagine in this situation, DVDT won't be zero, very close to zero. We will have a high DVDT. That's why DVDT at commutation, it's important in inductive-based solution, basically AC motors. The second DVDT that we need to be aware of, customers, you need to be aware of, it's basically this DVDT or static. It's more like an immunity. In our dataset, you will find it as a critical rate of rise of off-state voltage. It's basically while the TRIAC and SCR is off, there's no gate signal, the DVDT that will be affecting the TRIAC and can turn it on in a spurious manner, as I explained before. This is because of the circuitry surrounding, because of high switching speed devices around the TRIAC. And this is also another element that need to be considered when it comes to the design, and it's of course one of the challenges. So as I told you, this is a deep dive in this series QV and SV. And now you have understood what are the different challenges when it comes to the design of semiconductor-based solutions when controlling AC loads. QV, so the latest design, the latest offering is basically offering twice larger Q and QJ dynamic robustness. So above 50 volts microsecond at commutation, and static is around larger than 1,000 volts. Okay, so but let's understand what are actually designers doing right now in order to tackle this DVDT issue in real designs. So in real designs, what is basically used is a RC network that actually soften the transitions at the triac. Basically, as I put here in this example, is a resistor and a capacitor that will create a soften and let's say a softened DVDT at the triac, right? What happens is if we are allowing the DVDT to be higher with the new series QV and SV, we can actually reduce the size of the snubber, or actually in some applications, we can actually eliminate it completely and use the DVDT that the application will have or will suffer. Okay. There's another parameter you can find in the datasets that help us in the freedom to choose the right part number and also help us with the DVDT issue or DVDT challenge. It's called gate sensitivity versus DVDT robustness. This is an example I took from a dataset. It's a QV, no matter the voltage, 60 or 80, 16 amperes. And then we have the H, which will guide us to this gate sensitivity. The gate sensitivity is an important parameter because it will define the gate consumption, the gate needs, the gate current versus the DVDT. We know now that DVDT means bill of material cost because we are going to have a capacitor and resistor to tackle and to smooth these transitions, right? So it means, in other words, that if we use a low current part number, low gate current part number, like H2 in this particular case, we will have less robustness from the DVDT. We will have to use a larger snubber circuit. Whereas if we go into the H4 or H5, we will have more consumption from the gate. We will have a more robust situation against DVDT at commutation and this static one. We will have a more robust product. We can actually eliminate the snubber circuit around the triac. Okay. Just to make it more visual, we created this graph here saying we have the situation, actually designers you can use from H2 to H5, you see there in the y-axis. H2 is offering basically lower consumption thyristor, but of course on the left-hand side you will see the DVDT at commutation, and on the right-hand side you will see the DVDT as immunity. You will see that those values are much lower when using a much lower gate design or gate part number. Whereas if we go up in the curve, we will see that 50 milliampere devices can actually eliminate the need of snubber. And of course, the designers can choose freely which is the right part number for them to, let's say, tackle DVDT topic and also reduce gate consumption. So this is another level of degree, so another level of freedom that actually users can select, right, to have the most optimal device in their applications, whether more consumption at the gate, lower, larger RC network, or the other way around, higher gate current, and then a smaller RC network. So in order to understand how to select those part numbers, first we need to look at the product family. As I explained, we have Q, the focus families are Q, QJ, and QV. So here you can really have this part numbering. This is the first part, the first two letters, QV, for instance. Then you have the voltage, 60 or 80 or even 40. Just referring to the voltage, to the breakdown voltage, 400, 600, 800, 900, even up to 1000. Then the current rating between 0.8 up to 40, because we have even 40 amperes triacs, and also SSRs up to 70, right? You remember SSR are simpler devices that are not triacs, and we can actually go to the 70 amperes range. Then we have the package, which is one of the key highlights of Littelfuse as well, is that the package offering is quite large. We have from insulated packages and non-insulated packages, from the TO 220 in this case, up to the TO218, so 218, which is one of the insulated packages that offer also an advantage in some applications like heaters. And then the sensitivity, as I explained right now, we have different classes, Q, QJ, QV, but in these different classes, we also have another level of degree of freedom, which is basically the gate sensitivity. And here we can choose from H2 to H6, selecting the gate current that we want to allow in your design. And then last, we have the packet, basically tubable, nothing interesting. Okay, so just all in all, just to explain again, and just to, in a nutshell, to give you a clear view, what is QV and SV offering, we have a higher DVDT robustness, which actually help us to remove or just to reduce the size of the snubber. This means cost and size for the saving potential, right? Remember, QV series is offering twice QG and QJ dynamic robustness. We have in the QV and QJ family range, we have 150 junction temperature as a maximum temperature to be operated the semiconductor, which means we can decrease the size of the heatsink in comparison to Q. So our legacy family, 25%. So this is another level of, let's say, adjustment in the final products, which can help us to decrease the bill of material cost. Clip attach, this is something that I haven't presented in the training, but very important is that we have monolithic devices like QV that if we use wire bonding technologies for die attach, we may not have the same charge capability. And what we use is basically a clip attach technology, which allows us to go to higher charge currents and make the product very robust. And then last, as I explained right now, gate sensitivity. We have a large selection of components due to the freedom to choose gate sensitivity versus DVDT robustness. Remember, DVDT is one of the key challenges when it comes to the semiconductor-based solutions and will help us to eliminate the snubber circuit. It actually helps also designers to address the particular needs of its design. I hope this was good understood, and I was able to help you understanding the benefits of QV and SV series. We also have in the presentation sort of like a selection for heated controls, more resistive applications, more resistive loads, remember, where we basically help you and guide you through the selections, so the right part number selections. Just to name some, for coffee brewers, we have 60 amps, 25 amps with Q series and QJ series. Remember, QV series is higher. It offers a higher robustness in DVDT, but remember, resistive loads will not suffer from that much, of course. And you can actually use the QV in order to select the gate current sensitivity as well. But the first, let's say, selection for heat resistive base applications will be probably Q and QV series, right? We also have, which is one of the clear highlights of Littelfuse portfolio, is the TO218, which is insulated package. It actually comes with eyelet leads in one of the configurations. We have also the standard leads, but basically it's used for a growing market like tankless water heaters in residential arena, right? And we can go from the 25 to the 40 amp use. These are just an examples of how we can actually offer to these applications the products, but yeah, you can have it also in the handout. Also, when it comes more to non-resistive loads, we have LED dimmers, which is also one of the key applications we are addressing with Q, QJ, and QV families. And here we have even for low holding. So this is one series that is dedicated to LED dimmers that actually has a very low holding current that will prevent from flickering, from unstable operation. And we will have, let's say, the one dedicated product to that, right? The second one, the dimmer, it integrates actually the gate, so it's sort of like a diag that actually is integrated in the triac. and will help also designers to have a very compact design without the need of an external gate driver. Also for generic dimmers, more industrial area, we'll have up to 40 amperes. Also in this particular package that I told you, TO 200, 218, with ceramic insulation and up to 40 amperes, right? And then you see for some motor control and different appliances, we are offering also for sure the QV as a main runner. Okay, new releases. I just want to also explain you about what is coming. There's one product coming into the market that is called QS, that is self-protected, and it basically can be used directly at the mains and will also reduce the efforts from protecting from overvoltage protection. This QS series will come with a clamping function that will help you with the line transients that actually are described in the IEC 61000/45 that actually they need to be fulfilled, and this particular part actually are tested to do and fulfill these particular standards that are needed also to qualify your end product out there. This is an interesting product, of course. It's an interesting family. Sorry, I just clicked twice. Also from the new product release, as I told you, we are extending the portfolio of QV, and this is exactly where we are also offering here. So we are extending in different packages. So you will see different flavors here from voltages and currents up to the 25 amperes, but in different product ranges or in different packages ranges, right? Okay, this is for the QV. Quick hint on how to find those in our website. We have right now more than 1,300 products. So our portfolio is very broad, is very wide. And here this is a trick to find them quickly. So if you go to search function in our website and click Q or QJ, QV, and then you put the voltage, remember the first two numbers are actually for the voltage, then you will find them very quickly. And here, this is an example. I just click on Q80 and you will find different alternatives. Okay, yes, quick look on where we manufacture and where is located our facility for production. It's basically in Wuxi, where we have harmonized production line where we have the back end and the front end. So we produce the silicon, also the packaging there in Wuxi. And we are actually, let's say, offering from 5 inches to 6 inches wafer size, which is good enough for these kind of devices that are really very smooth. Okay, this is for the Q, QJ, and QV series. Now we're going to have a quick look into more industrial products named CX and MX series. Applications are similar, but also we are looking at things or different applications like UPS, soft starters, larger motors for sure from power, and also lighting. So first of all, we need to understand why we have like low power and then medium power different applications, or more an industrial segment for TRIACs and SSRs. So when we are looking at the point of connection in the electrical system, we will have our residential loads like coffee machines, LED dimmers, or ovens. They are going to be on the lower of the voltage category, so they are exposed to lower overvoltage classes, right? Whereas if we have a more industrial part, we'll be exposed to larger voltages like industrial drives, soft starters, or UPSs, right? Those will be in a different point of connection within the electrical system. And that's why we need higher voltages, high voltage classes from the thyristor perspective. Of course, there are other reasons like higher AC voltages, like higher motor drive voltages. But of course, this is one of the main reasons why we have an industrial range of thyristor products. Mm-hmm. So this is sort of like portfolio to understand where we are. These are the CX and MX series, more the legacy devices, where we have 50 active parts. And here we are really working on the CL, MN, and CN series with more than 100 active parts, optimized voltage classes from 1200, 1600, and above 2000. This is coming really with the two letters at the beginning, CL 1200, CM 1600, and CM above 2000. We have an increase of charge current capability, ITSM, that you can find in the dataset, and potential cost reduction. So if we compare two products from the legacy series to the new one, we have in our left-hand side CS45, a 1200 volts device, against our new device, CLA50. We have 20% cost reduction potential, 25% larger current, and 60% better thermal performance. So of course, this is the product to offer and to select in future designs. Very similar with this SOT227 product, comparing the MO90 against the CLA110, sorry. We have here lower conduction losses, so VT down 16%, 50% higher current, charge current, which is very important in industrial applications, because this will handle the inrush current, and 2.5 lower gate current, so consumption at the current, right? So we have better utilization of the chip area with the new series. Of course, it brings some additional benefits to the final users. So if we look at the product selection, how we should look at these and select them, as I told you, the first two letters will come with the voltage class, L for 1200, M for 1600, and N for 2000. Then we will have a chip class, chip current, and configuration and voltage and package. If we look first at the chip class, we have for this industrial series two different speeds, two different classes of chipsets to be used. So if we plot in a graph turn-off losses and conduction losses, we will see that the CA standard thyristors and the fast thyristors are differing in this, because the semi-fast are 3 times faster. Of course, they will have slightly higher conduction losses, but those can be used, and this is very unique also in our portfolio, that we can address applications where this frequency it's above 100 Hz, and with this semi-fast family, right? Keep in mind, if you have also some products that are running above 100 Hz, you can also use a faster thyristor. Okay, this is basically how we do it with our electronic radiation and annealing process. Then, and probably most importantly, is the configuration. Here for the industrial segment, we have E for single thyristor, MT for 3 quadrant triac, P for phase leg, and PD for phase leg and thyristor diode. How we can do configurations with triacs in a single package? It's because Littelfuse leads in chip design, and actually this helps us to have topologies in a discrete device. These are the different technologies that we have available: cathode on top, anode on top, and also gate connected, so anode gate connected and cathode gate connected thyristors. This variety, so these different choices help us to make more robust or more compact design, like in this example of the CLA60MT, which is basically a triac. As I told you, triacs can be a monolithic device or back-to-back SCR in configuration. In this case, it's a back-to-back configuration. And to make this product, we have selected CWN and CWPN. So an anode gate connected, anode gate connected, and cathode gate connected, which help us to reduce the efforts from the gate and have a common gate here in the package. This is very unique from Littelfuse and help us to make more optimums, help us to make more compact solutions, also reducing the efforts from the driving perspective. Okay. This is an example of a triac. Another example could be also one phase leg, so a full control bridge with thyristor. We will use, in this case, different chipsets. We will use a CWP and CWRP, which basically is both cathode gate connected, but one is cathode on top, the other one is anode on top. This helps us to maximize the silicon usage in the package and minimize the interconnections we need in the package, right? And that's why we actually can go to the 40 amperes with this package, because we have the chips, we actually have this architecture available, and we can actually increase and offer higher compactness at actually lower cost. So all in all, the benefits of industrial thyristor portfolio of Littelfuse is that we can go up to the 2.5 kilovolts, helping also designers to go to higher voltages, and also they minimize also the sun serial connections of TRIACs. Mostly this is important when we see designs when motor voltage is above 1 kilovolt, right? We have this chip class, as I told you, we have different speeds. We can trim the speed of the TRIAC and making them faster internal, right? For let's say attacking some applications where the grid frequency is higher than 100 Hz. We also have the chip designs. As I told you, we have 4 different designs that actually we can use to make more compact and more cost-efficient solutions, actually increasing the current rating of single discrete devices. Okay. And last, we have higher ITSM, as I told you. If we compare the QJ and QV series in comparison to in our industrial CL, CM, CN series, we can actually allow designers to go to higher ITSM, to higher inrush current, and this is very important as well in your final applications. So one of the, let's say, latest launch was this year, Q1 2025, was a higher current rating in TO247, 120 amperes, that can help you in designs where power density is important. And we see a clear market focus is STS, so it's bypassing UPS, where really you need a high power density, and here we can actually use it. We can actually use this part number to improve your design and improve your cost. This is my last slide, just to show where the center of design and production of these devices are for more industrial is here in Germany, where we are, where we basically have our factory in Lapperheim. We have more than 400 employees, and basically we design from the chip perspective and also the packages. And here we can, of course, help you with the design and support needed in your particular challenges. So all in all, just to make a short summary of what we have seen today, Littelfuse offers a comprehensive portfolio in SCR and TRIAC. Latest family QV and SV can reduce the slabber, that's below material cost, PCB size, and increase robustness when you are selecting a semiconductor-based solution for controlling AC electric loads. And in the industrial arena, you have a large industrial portfolio with focused families, CL, CM, CN, offer a robust, reliable, and compact solution. Thank you very much. That was my presentation. Thank you, Thomas.
Okay, thank you for your presentation. It was very cool, very good. So now, if you have any questions, you can contact us. You can ask if there's any question. I think it was very good overview at all the products from Littelfuse.
Thank you, Thomas.
Yes, and it was very good explained.
Thank you.